Iced coffee is one of the most popular drinks in the world. Starbucks, Tim Hortons, and Dunkin have each built signature recipes that blend premium beans, precise brewing methods, and unique flavor techniques to create their chilled bestsellers. Today, we go inside their process to see how the beans are roasted, how the coffee is cooled and poured, and how each brand adds its finishing touch to deliver the iced coffee millions of people drink every day. It all begins with the raw material, the coffee cherry. Starbucks sources 100% Arabica coffee beans, chosen for their nuanced flavor profile and natural sweetness. Arabica beans are grown at high altitudes, typically between 3,000 and 6,000 feet, in regions known as the Coffee Belt. This includes countries in Latin America, Africa, and Asia, particularly Colombia, Brazil, Ethiopia, Guatemala, Kenya, and Indonesia. Starbucks operates with an ethical sourcing framework called Coffee and Farmer Equity, or CAFE practices, which ensures that all green coffee is responsibly grown, ethically traded, and traceable. Once ripe, coffee cherries are harvested either by hand or machine, depending on the terrain and farm infrastructure. At origin, the first phase of processing begins almost immediately to prevent spoilage. There are two main processing methods, the washed process and the natural process. In the washed method, which Starbucks prefers for many of its core blends, the outer pulp of the cherry is removed using pulping machines. The beans are then fermented in water tanks to dissolve the sticky mucilage surrounding the parchment layer. This fermentation lasts between 12 and 48 hours and is followed by thorough washing and drying on patios or raised beds. In the natural process, cherries are dried whole under the sun and then hulled to remove all outer layers. Once dried to the correct moisture content, typically around 10 to 12%, the beans are hulled, graded by size and density, and bagged in jute sacks for export. Starbucks works closely with suppliers to ensure quality at this stage, often employing on-site agronomists and sustainability officers who audit farming and processing practices. The green coffee is then shipped in shipping containers to Starbucks roasting facilities located in the United States, Europe, and Asia. These massive facilities serve as the nerve centers for the company's coffee production. At the roasting facility, every shipment of green coffee undergoes an extensive quality inspection. Moisture analyzers measure the internal water content of the beans. Sieves and gravity tables are used to check for uniformity in size and weight, while UV lighting may be used to detect mold or defects. A sample of each lot is roasted in a small laboratory drum roaster, and the beans are cupped or taste tested by trained sensory experts. These cupping sessions are not casual tastings, but highly controlled evaluations that assess aroma, acidity, body, and flavor notes. Only green coffee that meets Starbucks' quality and consistency thresholds is approved for roasting. Roasting is perhaps the most transformative stage in coffee production. At Starbucks, roasting is performed in industrial drum roasters that can process thousands of pounds of beans per hour. The drum roaster is a large rotating cylinder heated by gas burners or electric elements designed to roast coffee evenly by maintaining constant motion and thermal distribution. As the green coffee enters the roaster, it begins to undergo endothermic and then exothermic reactions. Temperatures rise from ambient to over 200 degrees Celsius, initiating Maillard reactions between amino acids and sugars. This phase produces hundreds of volatile aroma compounds that form the signature flavor profile of roasted coffee. Each roast profile at Starbucks is meticulously programmed and monitored. Starbucks categorizes its coffees into 3 roast levels: blonde roast, medium roast, and dark roast. The precise duration and temperature profile of each roast is calibrated using software-controlled roasting curves. Sensors measure bean temperature, air temperature, and exhaust temperature in real time. At the end of the roast, The beans are discharged into a cooling tray equipped with high-powered fans and stirring arms that cool the coffee rapidly to halt further chemical reactions. After cooling, the beans are passed through destoners and magnets to remove any foreign material that might have entered the batch. They are then transported via enclosed pneumatic conveyors to temporary storage silos or directly to packaging lines. Starbucks utilizes an inert gas flushing system to preserve freshness. Bags of whole bean coffee are filled under a nitrogen blanket to displace oxygen and then hermetically sealed to prevent oxidation. Some products are vacuum packed, while others use one-way degassing valves that allow carbon dioxide to escape without letting oxygen in. In addition to whole beans, Starbucks also produces ground coffee, which involves a critical grinding step. Industrial roller grinders are used to achieve precise particle sizes depending on the final brewing method. For instance, espresso requires a fine grind, while French press requires a coarse one. The ground coffee is packaged immediately to reduce the risk of stalling. As with whole beans, nitrogen flushing and oxygen barrier packaging materials are standard. The packaging lines themselves are fully automated and capable of handling multiple SKUs simultaneously. Form-fill seal machines create bags from printed film rolls, fill them with measured doses of coffee, seal them with heat and pressure, and print lot numbers, expiration dates, and traceability codes. Each package passes through metal detectors and check weighers to ensure safety and regulatory compliance. From the roasteries, finished products are loaded onto pallets, stretch-wrapped, and barcoded for distribution. Starbucks operates regional distribution centers strategically located to support retail operations across North America and globally. Products are shipped via refrigerated or insulated trucks when needed to ensure quality remains consistent through transit. Every pallet is scanned upon arrival and departure, allowing Starbucks to maintain full traceability throughout its supply chain. Simultaneously, Starbucks produces the raw materials required for its in-store operations. These include portioned espresso pods, soluble coffee used in frappuccino bases, and instant beverages like Starbucks VIA. These products are made using either freeze-drying or spray-drying technologies. In the freeze-drying method, brewed coffee is frozen and then placed in a vacuum chamber where ice sublimates directly into vapor, leaving behind dry coffee crystals. This method preserves much of the coffee's aromatic compounds and is favored for high-end instant lines. Another vital component of Starbucks' industrial operations is its proprietary espresso roast and the pre-portioned espresso pods used in many stores. These pods are filled using high-speed rotary machines that dose, tamp, and seal the coffee under controlled conditions. Each pod is tested for fill weight, tamp pressure, and seal integrity. These pods are then boxed, barcoded, and shipped to stores alongside other operational supplies. Back at the retail level, each Starbucks store receives regular shipments from distribution centers, including roasted coffee, milk, syrups, toppings, and equipment parts. In-store coffee preparation is not improvisational. It is the final link in a deeply controlled manufacturing chain. Starbucks stores are equipped with calibrated espresso machines, automatic grinders, and digital timers to ensure that every beverage meets the company's exacting specifications. Baristas are trained to follow standardized operating procedures for pulling espresso shots, steaming milk, and assembling drinks to order. Even water quality is standardized. Starbucks uses triple filtration systems in its stores to remove chlorine, heavy metals, and organic contaminants from municipal water supplies. This ensures that the brewed coffee tastes the same whether you're in Seattle or Singapore. Equipment calibration, grinder burr alignment, and machine temperature profiles are monitored and adjusted regularly by technicians and store managers. Every cup of brewed coffee or espresso beverage is in effect the product of a vast industrial ecosystem designed for consistency, safety, and premium flavor. Behind the scenes, Starbucks maintains sophisticated digital infrastructure that collects data from roasting plants, packaging lines, and even point-of-sale systems to analyze trends and continuously optimize production schedules, inventory management, and waste reduction. As consumer preferences evolve, Starbucks continues to invest in research and development. The company experiments with new roast profiles, sustainable packaging materials, and emerging brewing technologies. Advanced sensors, machine learning, and IoT devices are increasingly integrated into both factory and store equipment to refine the precision of every step in the supply chain. The backbone of Tim Hortons' business is coffee, and their core blend, often referred to as the Always Fresh blend, is made from 100% Arabica beans. Arabica beans are chosen for their smoother, less bitter taste and their ability to offer nuanced flavor notes. These beans are sourced from a variety of coffee-growing regions around the world, particularly from South and Central America, including Colombia, Brazil, Honduras, and Guatemala. This sourcing model ensures consistency by blending different regional beans to balance acidity, body, and aroma. The beans are shipped as green, unroasted coffee in large jute sacks, packed into shipping containers, and delivered to Tim Hortons' central roasting facilities. Historically, roasting operations were closely tied to Canada, but as the brand has grown globally, roasting capacity has expanded and diversified into regional centers. Regardless of location, every roasting facility follows the same standardized protocol to maintain the flavor profile that Tim Hortons customers expect. Upon arrival, green coffee beans are first inspected for defects, such as insect damage, mold, or irregular size. Sophisticated sorting equipment, including density tables and optical sorters, ensures only the best beans enter production. Roasting is conducted in large-scale industrial drum roasters, which use gas-fired heat and constant motion to ensure even caramelization of the bean surface. The roasting process is highly automated and carefully monitored. The beans are heated to between 190 and 220 degrees Celsius, depending on the desired roast level. Tim Hortons is known for its medium roast, which balances brightness with a smooth body. During roasting, the beans undergo the Maillard reaction, a chemical process that creates hundreds of flavor compounds and the distinctive dark brown color of roasted coffee. After roasting, the beans are rapidly cooled in cooling trays using forced air to prevent over-roasting and lock in flavor. Once cooled, roasted beans are either packaged as whole bean coffee for select retail offerings or ground to precise specifications using industrial burr grinders. Particle size is tightly controlled to optimize extraction during brewing. The ground coffee is then flushed with nitrogen and sealed in laminated foil packaging to preserve freshness. These packages are boxed, palletized, and shipped to regional distribution centers where they await delivery to individual Tim Hortons restaurants. At the store level, Tim Hortons follows a carefully engineered brewing protocol. Ground coffee is delivered in pre-measured, vacuum-sealed foil packets, ensuring consistency in volume and grind size. Each packet is loaded into commercial-grade drip brewers, which are calibrated to deliver a specific water temperature, volume, and contact time, usually around 93 degrees Celsius and 4 to 5 minutes of brew time. The water used is filtered using in-store triple filtration systems to remove off flavors and ensure uniform taste across all locations. After brewing, coffee is held in thermal carafes and discarded after 20 minutes if not served, reinforcing the Always Fresh brand promise. While coffee is the flagship product, Tim Hortons is equally famous for its baked goods, especially donuts, muffins, bagels, and the beloved Timbits. Unlike traditional bakeries that make everything from scratch on site, Tim Hortons uses a centralized frozen dough system. This model allows the company to maintain strict control over ingredient sourcing, product consistency, and food safety, regardless of geography. The journey begins in massive baking and dough production plants, where key ingredients, flour, sugar, oil, milk powder, leavening agents, and stabilizers are blended in giant horizontal mixers. Flour is stored in silos and piped pneumatically into mixers in precise quantities. Other dry ingredients are batch dosed using computerized control systems. For yeast-raised products, sponge and dough fermentation methods are used, where a pre-ferment is made first, then mixed with the final dough for better flavor and texture. Once the dough reaches the proper elasticity and hydration, it is sent to forming lines. In these automated production lines, the dough is sheeted, cut, and shaped into donuts, timbits, quenelles soissons, or muffin bases using rotary cutters and die presses. For filled products, injection systems deposit jam, custard, or chocolate fillings at high speeds. The shaped dough is then partially proofed, allowed to rise in warm, humid chambers until it achieves optimal volume. At this point, the items are flash frozen in spiral freezers, which use blasts of cold air to bring the core temperature below -18 degrees Celsius in under 30 minutes. This locks in moisture and stops yeast activity, preserving the dough in a ready-to-bake state. The frozen products are boxed and placed onto pallets, which are stretch-wrapped and loaded into refrigerated trucks. These products are delivered regularly to Tim Hortons restaurants, where they are stored in on-site walk-in freezers. In each store, baking takes place throughout the day in cycles to meet demand. Staff remove the frozen dough, place it on baking trays, and allow it to finish proofing in temperature and humidity-controlled proofers. Once ready, the items are baked in convection ovens or deep-fried in commercial fryers, depending on the product. Donuts are often fried, then glazed or coated with toppings using automated glazing equipment or manual dipping. Muffins, scones, and cookies are oven-baked and cooled on racks before serving. All baked goods are time-stamped and held in display cases for a maximum number of hours, usually 4 to 6, before being discarded. This ensures that customers always receive a product that is freshly baked and at peak quality. Beyond coffee and baked goods, Tim Hortons also operates a sophisticated food assembly line for breakfast sandwiches, soups, and other hot offerings. Most of the components, egg patties, bacon, sausage, cheese slices, biscuit, and English muffin bases, are produced off-site in high-capacity food manufacturing plants. Egg patties are typically made using liquid whole eggs poured into silicone molds and cooked in steam ovens. Sausage is formed, grilled, and flash frozen, while bacon is par-cooked and vacuum-packed. All of these components are delivered frozen to Tim Hortons stores, where they are reheated using convection ovens, panini presses, or rapid cook devices. Sandwiches are assembled to order using standardized build charts to ensure consistent ingredient quantities and presentation. Soup bases arrive frozen in boilable plastic bags. These are placed in rethermalization tanks that heat the soup via hot water immersion to safe serving temperatures. Every step in the in-store process, from coffee brewing to sandwich assembly, is governed by strict standard operating procedures developed by the company's operations and culinary teams. Employees are trained using visual job aids, time temperature checklists, and digital training modules. Food safety is ensured through a combination of regular audits, real-time temperature monitoring, and strict sanitation protocols. Once the product is served, the final step in the production journey is customer feedback and data capture. Tim Hortons collects enormous volumes of sales and operational data from its restaurants through its point-of-sale systems. This data is analyzed centrally to identify purchasing trends, optimize menu items, adjust production forecasts, and inform the development of new products. In essence, the entire supply chain is a closed-loop system, with consumer behavior feeding back into manufacturing and distribution planning. Behind the warmth and familiarity of a Tim Hortons location is a deeply complex industrial engine. From green coffee beans sourced on mountain farms to robotic dough shapers cutting out donut rings, every element of the process has been engineered for scale, consistency, and freshness. While the customer might only see a smiling barista and a hot cup of coffee, each interaction is powered by global sourcing logistics, frozen supply chain systems, high-capacity roasters, and automated food production facilities that work 24 hours a day to maintain the brand's reputation. The story of Dunkin's coffee begins in the lush, tropical regions of the world, where the climate, elevation, and soil conditions are ideal for growing coffee. Dunkin exclusively uses 100% Arabica beans, known for their smooth flavor and lower bitterness compared to Robusta. These beans are sourced primarily from Central and South America, including countries like Colombia, Honduras, Brazil, and Guatemala. Additional supply may come from East Africa or Asia-Pacific regions, depending on seasonal availability and blend requirements. Dunkin partners with long-standing suppliers who operate under strict quality assurance and sustainability standards. These relationships are critical as they allow Dunkin to secure consistent flavor profiles across thousands of stores. Coffee cherries are harvested either by hand or machine, depending on the region. Once picked, the beans are processed using the wet or washed method, where the pulp is removed mechanically and the beans are fermented to remove mucilage, then washed and dried. Once fully dried, the beans are hulled to remove the parchment layer, graded by size and weight, and sorted for defects using a combination of sieves, density tables, and optical sorting systems. High-quality, defect-free beans are bagged in breathable jute sacks, loaded into containers, and shipped to Dunkin's roasting partners in North America. Upon arrival at the roasting facility, green coffee beans undergo extensive quality inspections. Moisture content is measured to ensure levels are between 10 and 12%, which is critical for optimal roasting. The beans are also evaluated for physical uniformity and potential contaminants. Sample batches from every shipment are roasted in laboratory sample roasters and subjected to cupping, a formal tasting method used to evaluate aroma, acidity, body, and flavor consistency. Dunkin's quality assurance team ensures that every batch of green coffee aligns with the company's proprietary flavor specifications before it can proceed to the roasting stage. Dunkin's industrial roasting is performed in massive batch roasters or continuous drum roasters capable of handling several tons of beans per hour. Each Dunkin roast follows a precise time temperature curve that is unique to its specific product line, whether for hot brewed coffee, espresso, or cold brew concentrate. The roasting process begins as the beans are fed into a rotating drum, preheated to temperatures between 180 and 210 degrees Celsius. As the beans absorb heat, they pass through a sequence of physical and chemical changes. Initially, the beans lose moisture and turn yellow, then brown, as Maillard reactions and caramelization processes develop their complex flavor compounds. During roasting, sensors continuously monitor internal bean temperature, exhaust air temperature, and pressure. Operators use digital interfaces to control airflow, drum speed, and burner output, allowing them to adjust the roast in real time. Many modern roasting facilities also utilize artificial intelligence or machine learning systems that analyze bean behavior and adjust roast parameters for maximum consistency. Dunkin's traditional roast tends to fall in the medium-dark range, designed for a rich, smooth body with minimal acidity, ideal for high-volume, fast-paced service environments. At the end of the roast, beans are discharged from the drum into a cooling tray. Forced ambient air is circulated by high-speed fans to rapidly drop the temperature and stop further development. Cooling takes place within 2 to 3 minutes to preserve aromatics and avoid over-roasting. Cooled beans are then sent through magnetic separators and destoners to remove any ferrous or dense foreign materials. After cleaning, the roasted coffee moves to degassing silos, where it rests for 12 to 24 hours. During this period, carbon dioxide naturally released from the beans dissipates. This step is crucial, especially for whole bean packaging, to prevent bloating or bursting of sealed bags. After degassing, the beans are sent through commercial-grade roller grinders. These machines allow for highly controlled particle size reduction, critical for consistent brewing. Dunkin uses different grind profiles for various applications. Coarser grinds for drip coffee, finer grinds for espresso pods or espresso machines, and ultra-fine grinds for cold brew concentrates. Grinders operate under real-time feedback loops to adjust burr pressure and maintain target particle distributions, measured using laser diffraction analyzers or sieve shake systems. Once ground, coffee is packaged using fully automated form-fill-seal machines. Dunkin's ground coffee is typically packed in laminated foil pouches with a one-way degassing valve. This valve allows CO2 to escape without allowing oxygen to enter, preserving freshness. Each pouch is flushed with nitrogen prior to sealing to displace ambient oxygen and minimize oxidation. Ground coffee may also be packed into vacuum-sealed bricks, multi-pound food service bags, or K-cup pods. In the case of K-cup production, the ground coffee is dosed into plastic pods lined with filter paper, then sealed with foil tops. Each pod is nitrogen flushed, sealed, and laser coated for traceability. Dunkin operates several distribution centers that manage inventory, track expiration dates, and coordinate deliveries to retail locations. Coffee products are stored in climate-controlled environments to protect against humidity and temperature swings that can degrade quality. Orders from franchisees are fulfilled via just-in-time inventory models to minimize waste and maximize product rotation. Palletized goods are shipped via dedicated food service carriers in dry trucks to locations across North America and international markets. At the store level, Dunkin's brewing systems are engineered for efficiency, speed, and consistency. The most common brewing system in Dunkin stores is the Bun Commercial Drip Brewer, which is calibrated to specific temperature, flow rate, and brew time specifications. Water is heated to between 90 and 96 degrees Celsius and sprayed evenly over the pre-portioned coffee grounds contained in flat-bottom filter baskets. Dunkin's coffee comes pre-measured in sealed foil pouches, each designed to brew a standard volume, such as 64 or 128 ounces. This eliminates measurement errors and speeds up preparation. Each brewed pot is held in thermal carafes or air pots for a maximum of 18 to 20 minutes before it is discarded. This policy ensures that guests receive fresh tasting coffee at all times. Cold brew is prepared by steeping coarse ground coffee in cold filtered water for 12 to 18 hours in food-grade brewing vessels. Once extracted, it is filtered, diluted, and held under refrigeration until served. Espresso is prepared using automated or semi-automated machines, often from brands like La Marzocco or Thermoplan. These machines use programmable dosing and pressure profiling to produce consistent shots from Dunkin's proprietary espresso blend. Each store uses filtered water systems to ensure consistent brewing quality across diverse water supplies. Minerals and chlorine are removed through carbon filters and reverse osmosis membranes. The calibration of grinders, brewers, and espresso equipment is overseen by certified technicians, and maintenance schedules are strictly enforced to prevent flavor drift or equipment failure. Beyond coffee, Dunkin stores also prepare beverages such as lattes, macchiatos, refreshers, and flavored iced drinks using base syrups and dairy products delivered through the same supply chain infrastructure. Flavored coffee syrups and sweetened condiments are pre-dosed for standardization. Beverages are assembled in branded cups and labeled with customer names using digital screens integrated with the store's POS and mobile ordering systems. Dunkin also tracks sales, quality metrics, and waste data through digital dashboards that are monitored at both the store and corporate level. This real-time analytics system feeds data back into the sourcing and roasting operations. If a region starts showing a preference for darker roast or cold brew, the manufacturing side can shift production volumes accordingly. As consumer expectations shift, Dunkin continues to innovate in sustainability and packaging. Recyclable K-Cups, sustainable sourcing initiatives, and expanded use of Rainforest Alliance certified beans reflect the brand's effort to evolve its industrial model while maintaining flavor consistency. Automation, machine learning, and data analytics are being integrated deeper into the roasting and distribution pipeline, further enhancing forecasting and inventory optimization. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple: water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, the glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, the sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees C and 22 degrees C, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection, and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios. For Taco Bell, it all starts with ingredient sourcing. Each core component, beef, chicken, tortillas, cheese, lettuce, beans, and sauces, is handled as a separate production category. Take the seasoned beef, for instance, one of the most widely used ingredients in Taco Bell's product lineup. The ground beef used in their tacos and burritos is not prepared in restaurants from raw cuts, but is instead pre-cooked and seasoned at dedicated meat processing plants. These USDA-inspected facilities receive large quantities of lean beef trimmings from approved slaughterhouses. The trimmings are first ground to a standardized size, then cooked in continuous belt cookers or steam-jacketed kettles, where they are combined with a proprietary spice mix and water. This seasoned beef mixture includes salt, paprika, garlic powder, onion powder, chili pepper, and food-safe thickeners such as maltodextrin or modified cornstarch, which help maintain moisture and consistency during reheating. Once cooked and blended, the meat is rapidly cooled using blast chillers to bring it down to a safe storage temperature, typically under 40 degrees F. It's then sealed into vacuum-packed, food-grade plastic pouches, often in 5 to 10 pound portions, and shipped to Taco Bell locations in refrigerated trucks. Reheating in the restaurant is done via hot water immersion. Staff place sealed pouches of seasoned beef into temperature-controlled water baths or steam tables where they are brought up to a serving-safe temperature of approximately 165 degrees. Once heated, the pouches are opened and the beef is transferred to metal steam pans for assembly line use. This system ensures consistent flavor and safety while eliminating the need for on-site raw meat handling or complex cooking. The chicken used in Taco Bell's items, such as the chicken quesadilla or chicken soft taco, is also pre-cooked and seasoned off-site. Chicken breast or thigh meat is cooked via steam ovens or flame grilling conveyors, chopped into small cubes or shreds, and seasoned with blends that may include lime, cumin, garlic, or smoke flavor. Like the beef, it is packed, chilled, and delivered in vacuum-sealed bags, ready for simple rethermalization in store kitchens. Beans represent another foundational element of Taco Bell's menu. However, the refried beans used in tacos and burritos do not begin as whole-cooked pinto beans in store kitchens. Instead, Taco Bell utilizes dehydrated bean flakes or paste that is shipped in dry form to each restaurant. In-house preparation involves mixing the dehydrated bean base with hot water in large mixing containers. The hydration process usually takes about 30 minutes, resulting in a thick, smooth, refried bean mixture that mimics the flavor and texture of slow-cooked beans without the need for hours of simmering. Taco shells, soft tortillas, and flatbreads used in items like chalupas or gorditas are all factory-produced in massive quantities. Tortilla manufacturing plants produce millions of units per day using high-capacity presses and continuous baking ovens. For crunchy taco shells, corn masa dough is rolled flat, cut into circles, then shaped into taco forms using conveyor-mounted clamps that hold the shells in a U shape while passing through hot oil fryers. Soft flour tortillas are rolled, pressed, and baked in tunnel ovens before being cooled, stacked, and packaged. All tortilla products are delivered to Taco Bell stores in bulk quantities, often stacked in wax-lined boxes or plastic-wrapped bundles. Shredded cheese, typically a blend of cheddar and mozzarella known as cheddar melt or low moisture cheese, is also prepared off-site. Dairy plants shred and anti-cake the cheese using potato starch or cellulose, then bag and cold store the product in 5-pound bags. Lettuce and tomatoes are sourced from large-scale produce distributors. Lettuce is pre-shredded and washed in chlorinated water systems before being sealed in bags and shipped cold. Tomatoes arrive diced and ready to use, stored in resealable containers. This product is handled under tight temperature controls to minimize spoilage and maintain food safety. One of the key hallmarks of Taco Bell's food production system is the precise engineering of its sauces and flavor components. From fire sauce to nacho cheese and avocado ranch, each condiment is mass-produced in food processing plants using batch tanks, emulsifiers, and thermal pasteurizers. These sauces are hot-filled into flexible pouches or plastic bottles and shipped to restaurants in cases. The nacho cheese sauce, for instance, arrives in large plastic bags that are reheated in warming trays and dispensed into smaller serving containers or squirt bottles for assembly line use. With all core ingredients delivered and prepared, the in-store operations at Taco Bell are focused primarily on assembly, heating, and final presentation. Kitchen layouts are designed with efficiency in mind. Stations are arranged for maximum throughput, with hot holding units for proteins, refrigerated bins for cold ingredients, and toasting presses or microwave ovens for final heating steps. Each employee is trained to follow strict build charts that dictate the exact weight, portion, and layering sequence for every menu item. Consider the construction of a simple, crunchy taco. An employee grabs a pre-fried taco shell, scoops in 1.5 ounces of reheated seasoned beef, sprinkles on a portion of shredded cheddar cheese, and tops it with shredded lettuce. The taco is placed in a pre-formed cardboard holder or paper wrap and slid down the assembly counter. Another team member may bag the item along with others in the order and hand it off to the customer or delivery system. Each item is constructed in under 30 seconds, often with multiple staff working in tandem to complete combo meals. More complex items, like the Crunch Wrap Supreme or Quesarito, involve multiple cooking surfaces. The Crunch Wrap begins with a large flour tortilla laid on a prep station. A portion of seasoned beef, nacho cheese sauce, a crunchy tostada shell, sour cream, lettuce, and tomatoes are layered precisely. Then the tortilla is folded inward in a 6-sided pattern. The folded wrap is then transferred to a clamshell grill, where it is toasted for 15 to 20 seconds on each side, creating a sealed, crispy exterior that holds all components inside. Timing and temperature control on these grills are essential to ensuring consistent texture and flavor. Items that require melting, like the chicken quesadilla, are prepared on flat-top presses, where cheese and sauce are sandwiched between tortillas and grilled until the inside reaches the right melt consistency. The burrito category includes both cold-rolled and hot-pressed variants, some of which are briefly steamed in microwave units to soften the tortillas for better folding. Each order flows through the point-of-sale system into digital kitchen displays or printed tickets that guide the team through item prep. Digital timers and alarms notify staff when holding times are exceeded. For example, beans and proteins can only be kept in steam trays for a certain number of hours before being discarded. This food safety timing is enforced by on-screen alerts and regular audits. Taco Bell also operates with tight allergen and cross-contamination protocols. Ingredients like eggs and gluten are kept in color-coded bins, and staff are trained to change gloves and utensils when handling allergen-sensitive items. Regular hand washing, surface sanitizing, and utensil swapping are monitored to comply with food safety regulations. Waste management is another component of the behind-the-scenes operations. Ingredient overages, expired pouches, and unsold food must be recorded, discarded, and tracked to help corporate operations refine inventory planning. In larger, high-volume locations, daily food waste is separated by category and used to adjust future order quantities and reduce spoilage. The speed and consistency of Taco Bell's service are powered by centralized prep, strict protocols, and kitchen ergonomics. Unlike traditional made-from-scratch restaurants, Taco Bell excels in reassembly-based cooking. Nearly every component is pre-cooked or pre-processed before entering the store, then finished through heating, assembling, and packaging. Distribution plays a huge supporting role. Taco Bell's supply chain is managed by logistics partners who oversee refrigerated warehouses, regional distribution hubs, and real-time inventory tracking. Each store receives multiple weekly shipments in temperature-controlled trucks with organized inventory manifests. Cold goods, frozen ingredients, and dry stock are unloaded and stored according to first in, first out practices to ensure product rotation and freshness. The journey of every Chick-fil-A meal begins at the sourcing stage. The star of the menu, the boneless chicken breast filet, is sourced from select poultry suppliers in the United States. These suppliers raise chickens under strict guidelines that align with Chick-fil-A's specifications for breed, weight, and overall meat quality. The birds are harvested, deboned, and portioned into consistent-sized breast fillets. Unlike many competitors who pre-bread or par-fry their chicken at a central facility, Chick-fil-A's chicken breasts are shipped raw to each restaurant in refrigerated containers. This raw chicken is never frozen, allowing for a level of freshness that the brand believes enhances taste and texture. Each boneless, skinless chicken breast is trimmed and pre-marinated at the processing facility in a proprietary blend of seasonings and pickle juice brine. This marinade is designed to infuse moisture and flavor deep into the meat, enhancing its juiciness and imparting the slightly tangy profile that Chick-fil-A fans recognize instantly. Once marinated, the raw, unbreaded fillets are vacuum-packed and shipped cold to the restaurants on a tightly managed logistics schedule. At the store level, food preparation is more involved than in many other quick-service restaurants. Chick-fil-A maintains what could be called a semi-scratch kitchen model. That means that while certain ingredients are prepared off-site, a large portion of the cooking, including the breading, frying, and assembly, is done entirely in-house, by hand, and to order. Once the marinated chicken arrives at the store, it is stored in walk-in refrigerators until needed. When an order is placed, staff members retrieve the raw fillets and manually bread them in real time. This process occurs at designated breading stations. Employees take the chicken from the cooler, dip it in a liquid egg wash, and then dredge it in a dry flour mixture that includes a carefully balanced blend of spices, paprika, black pepper, salt, and other proprietary seasonings. The breading is done using a method known as pressure packing, where the breading is pressed firmly into the meat using a specific motion and timing to ensure even coating and adhesion. Excess flour is shaken off, and the chicken is immediately sent to the fryer. Chick-fil-A uses pressure fryers, which are similar in design to commercial deep fryers, but operate under sealed, pressurized conditions. This allows the chicken to cook faster and more evenly while locking in moisture. Each fryer basket is lowered into preheated oil, usually peanut oil, selected for its high smoke point and clean flavor, and cooked at a consistent temperature. The pressure fryer ensures the chicken reaches a safe internal temperature of 165 degrees Celsius, while forming a crisp, golden brown crust that adheres tightly to the fillet. The total cooking time is typically around 4 to 5 minutes, depending on the thickness of the chicken. Meanwhile, the buns for the classic Chick-fil-A sandwich, soft, white hamburger buns, are stored in sealed bags and toasted on a flat-top grill or vertical toaster just before serving. Each bun is lightly buttered, toasted until golden brown, and then used as the base for sandwich assembly. A single dill pickle slice, or sometimes two, is added directly to the bottom bun before the hot, freshly fried chicken fillet is placed on top. This simplicity is intentional. The standard sandwich contains no sauce, no lettuce, no tomato, just chicken, pickles, and bun. The clean flavor profile helps highlight the taste of the seasoned chicken. For other menu items, such as the spicy chicken sandwich or deluxe versions, the process is similar, but may include spicy seasoning in the breading or added toppings like lettuce, tomato, and cheese. These variations are all built on the same foundation of freshly breaded and fried chicken. In addition to sandwiches, Chick-fil-A's menu includes items like chicken nuggets and chicken strips, which are made from the same chicken breast meat but cut into smaller portions. Nuggets are breaded and fried using the same process as the sandwiches, but are cooked in separate baskets to ensure optimal timing and doneness. They are drained, portioned, and served with a variety of sauces, including Chick-fil-A sauce, Polynesian, barbecue, and more. These sauces are mass-produced in centralized facilities and shipped to stores in portion-controlled packets or squirt bottles. One of the most labor-intensive and visually distinctive products is Chick-fil-A's waffle fries. These are made from US-grown potatoes, typically russet or similar varieties. The potatoes are processed at off-site facilities where they are washed, peeled, and sliced using a specialized corrugated blade that cuts the signature waffle pattern. The fries are par-cooked, lightly fried or blanched, then frozen for shipment. At the store level, fries are deep-fried in vegetable oil until crispy and golden brown, then salted and served in paper fry cartons. Timing is critical, as fries can quickly lose texture if overcooked or held too long under heat lamps. Salads and wraps are also a major part of the menu and are made fresh daily in each restaurant. Located tongs. Refrigeration zones are monitored with temperature logs, and hand washing is mandatory at regular intervals throughout each shift. Inventory is tracked digitally using integrated systems that forecast usage patterns based on sales data. Deliveries arrive several times per week in refrigerated trucks managed by regional distributors. Ingredients are unloaded and placed into designated storage zones, dry goods in pantry racks, dairy in walk-in coolers, and frozen items in freezers. First in, first out procedures are strictly followed to ensure freshness and minimize waste. While Chick-fil-A emphasizes hospitality and service, its operational core is deeply industrial. Behind the smiling team members and friendly service is a kitchen run with the efficiency of a well-oiled machine. Staff are trained for weeks on food safety, equipment handling, and assembly line execution. Managers use real-time kitchen display systems to track order times, ingredient usage, and customer wait durations. Every Burger King sandwich begins with one core ingredient: beef. The signature flame-grilled beef patties used in Whoppers and other burgers are produced off-site in USDA-approved meat processing facilities. These patties are made from ground beef sourced from large-scale cattle operations, typically using a blend of trimmings that provide the right balance of fat and lean meat for flavor and texture. Burger King uses frozen beef patties that arrive in individually separated stacks, typically flash frozen immediately after being formed and shaped at the plant. The patties are not seasoned before shipping. Instead, they rely on Burger King's flame grilling process to impart their unique smoky flavor. Each patty is shaped to standard specifications, precise diameter, and thickness, to ensure even cooking across various store locations. Once frozen and packed, the patties are delivered to Burger King restaurants in refrigerated trucks, along with other temperature-sensitive ingredients. The distinguishing feature of Burger King burgers is the use of a flame broiler. Unlike griddle-based fast food systems that fry patties on a flat top, Burger King uses a gas-fired conveyor broiler. This piece of equipment features metal grates that carry raw, frozen beef patties across an open flame. As the patty travels down the conveyor, the bottom is seared by the grate, while flames rise through the spaces to cook the surface. This creates the familiar grill marks and smoky char flavor that Burger King promotes as flame grilled. The time, heat, and flame intensity are precisely calibrated for each patty size, and sensors ensure consistent performance throughout the day. After cooking, the hot patties are held briefly in a heated chute before being placed on sandwiches made to order. Holding time is carefully limited to preserve moisture and flavor, and any unused patties are discarded after a preset interval, typically no more than 10 minutes. Meanwhile, buns are sourced from regional bakeries that contract with Burger King. These suppliers follow detailed specifications for bun size, density, color, and sesame seed coverage. Burger King buns are delivered in plastic bags to each store and kept in dry storage until use. Before assembly, buns are toasted using vertical toasters or clamshell-style contact toasters that give the bread a lightly browned, crisp surface. This toasting step is important not only for flavor and texture, but also to prevent the buns from becoming soggy when layered with hot ingredients. Vegetables like lettuce, tomatoes, and onions are delivered pre-washed and pre-cut by produce suppliers, reducing the amount of prep work required in store. Iceberg lettuce is shredded into fine strips, tomatoes are sliced into thick rounds, and onions are cut into rings. These items are packed into food-grade containers and stored in the walk-in cooler. In the kitchen, they are portioned into smaller bins and placed on refrigerated make lines for quick access during sandwich assembly. The Whopper, Burger King's flagship sandwich, is a prime example of this orchestrated system. The build begins with a toasted sesame seed bun, followed by a cooked beef patty fresh from the broiler. The bottom bun gets a layer of mayonnaise, followed by the patty, lettuce, tomato, sliced onions, pickles, ketchup, and the top bun. Each ingredient is placed in a specific order to control how the sandwich holds together and delivers flavor with each bite. The finished sandwich is wrapped in a branded wrapper and handed off to the customer, typically in under a minute from the time it was ordered. Chicken items like onion rings are also prepared in deep fryers. Frozen fries are delivered pre-cut and par-cooked, meaning they have already been partially fried at the processing facility. In the restaurant, fries are cooked from frozen to final crispness in fryer baskets at around 350 degrees. Once golden and crispy, they are tossed with salt and served in paper fry cartons. Onion rings and other specialty sides follow the same procedure, with slight differences in cook time and seasoning. Beverage operations are handled using a combination of soda fountains, iced drink machines, and occasionally coffee brewers. Fountain drink systems are supplied by soft drink manufacturers and connect bag-in-box syrup containers that blend flavored syrup with a dairy base and churn the mixture into a soft serve texture. These machines require regular cleaning and calibration to maintain hygiene and consistency. Breakfast at Burger King involves its own set of processes. Items like the croissant-wich or breakfast burrito start with eggs, sausage, ham, bacon, and cheese, all of which are prepared in-store. Liquid eggs or pre-cooked egg patties are stored cold and cooked on flat-top grills or microwave steamers. Sausage patties and bacon strips are pre-cooked at the factory and reheated in microwave ovens or clamshell grills. Croissants, biscuits, and muffins are toasted or warmed before assembly. The result is a hot, made-to-order breakfast sandwich built to brand specs. All ingredients in a Burger King kitchen are stored and rotated using first-in, first-out inventory systems. Refrigerated and frozen goods are kept in walk-in coolers and freezers, while dry ingredients, such as condiments, packaging, and buns, are stored on wire racks in designated stock areas. Each location receives scheduled deliveries several times per week from regional distribution centers that consolidate goods from multiple suppliers. In terms of food safety and quality assurance, Burger King enforces strict operational guidelines. Cooking temperatures are continuously monitored with digital thermometers. Meat must reach designated internal temperatures, generally 165 degrees for chicken and 155 degrees for beef, before being served. Holding times for cooked items are carefully tracked using timers. Once expired, items are discarded to ensure freshness and safety. Sanitation plays a crucial role as well. Fryer oil is filtered and replaced regularly to prevent flavor degradation. Food contact surfaces are sanitized between shifts. Employees are trained to change gloves frequently, wash their hands according to standard procedure, and avoid cross-contamination between raw and cooked foods. Temperature logs are maintained daily, and stores are audited by corporate teams for compliance. Digital systems also support the kitchen operation. Each order is displayed on kitchen monitors that guide employees step by step through preparation. Timers indicate how long each cooked item has been held. POS systems automatically update inventory data based on sales, helping managers reorder stock as needed and minimize food waste. Packaging is another important piece of the Burger King operation. Sandwiches are typically wrapped in branded wrappers that are color-coded by product type to make identification easier. Burgers may also be served in clamshell boxes or paper sleeves, depending on local standards. Fries are packed into branded cartons, and combo meals are bagged in paper bags, along with napkins, straws, and condiments. All packaging is designed for speed, functionality, and heat retention. To keep up with changing tastes and competition, Burger King frequently introduces limited-time offerings. These often involve new flavor combinations, special sauces, or modified versions of existing sandwiches. When an LTO is launched, stores receive new ingredients, updated build charts, and promotional materials. Staff are trained on the new product and briefed on its preparation and assembly. Once the promotion ends, the remaining stock is used up or removed from the line. It all begins with the chicken itself, fresh, never frozen, and selected according to strict specifications that have been standardized over decades. At the heart of KFC's fried chicken production is consistency, and that starts with sourcing poultry from highly regulated farms, often contracted directly to supply birds that meet stringent criteria for weight, size, age, and health. These chickens are typically raised under controlled conditions, with monitored feeding schedules and veterinary oversight, ensuring uniformity in muscle development and fat content. Farmers work closely with the suppliers to deliver birds that fall within the optimal range for processing, which generally hovers around 4 to 6 pounds per whole bird, depending on the regional market. Once the birds arrive at the poultry processing plant, they undergo a sequence of highly regulated steps designed to transform them into the individual cuts used in KFC's iconic fried chicken buckets. The first step is stunning and slaughter, where automated systems humanely render the birds unconscious before they are swiftly slaughtered. This is followed by scalding, immersing the carcasses in warm water to loosen feathers, and defeathering using a mechanical plucking system that employs rotating rubber fingers to strip feathers from the skin without damaging the flesh. The next phase involves evisceration, where internal organs are removed through a series of automated mechanical arms and cutting systems. Inspectors, both human and digital, examine the internal cavities for any signs of disease or contamination. The birds are then washed thoroughly in a series of chilled water baths and antimicrobial sprays to reduce surface bacteria. After this, the carcasses are chilled rapidly, often through immersion in ice water or air-chilling tunnels, to bring the internal temperature down to safe levels before further processing. With the whole birds chilled and inspected, they are transferred to the cutting line. This is where the chicken is portioned into the familiar cuts used in KFC recipes: drumsticks, thighs, breasts, wings, and occasionally rib portions, depending on the market. High-speed blades and vision-guided robotic systems ensure that each piece is cut uniformly. Some facilities even use X-ray and laser-guided cutting to detect bone structure and fat lines, optimizing yield and reducing waste. The chicken pieces are then sorted by size and weight, ensuring every batch has a consistent mix for packaging and preparation. After cutting, the chicken is placed into sanitized plastic totes or stainless steel trays and sent to the marination area. This is a crucial step that lays the foundation for KFC's signature flavor. The original recipe chicken is soaked in a wet brine that typically includes water, salt, and phosphate-based tenderizers to enhance juiciness and flavor retention. The chicken is placed into large tumblers, rotating drums with paddles inside that gently agitate the meat to ensure thorough penetration of the brine. This marination process typically lasts for a fixed duration, anywhere from 30 minutes to several hours, depending on the specific product line. But marination is just the beginning. What truly sets KFC apart is the breading process, a meticulously controlled step where secrecy and technique intertwine. The chicken is removed from the brine and allowed to drain slightly before being transferred to the breading stations. The breading mixture, known for its secret blend of 11 herbs and spices, is kept under strict control. At the manufacturing level, this seasoning is produced in centralized spice blending facilities, measured with pharmaceutical-level precision, and shipped to stores or distribution centers in tamper-proof bags. Operators follow a carefully choreographed breading procedure known as the 7-to-10-7 method. First, the chicken is placed into a flat metal pan with the dry breading mix and hand-tossed 7 times in a specific pattern to ensure an even coating. Then the pieces are compressed down into the breading mixture for 10 seconds. This step helps the coating adhere and creates the famous textured crust. Finally, the pieces are shaken 7 more times and arranged neatly onto perforated trays for the next stage. This manual method, despite being labor-intensive, is a cornerstone of KFC's identity and helps achieve the distinctive craggy exterior that customers recognize instantly. Once breaded, the chicken is moved to the fryers. KFC uses high-capacity pressure fryers, commercial machines that resemble deep fryers, but with tightly sealed lids that allow cooking under pressure. This equipment is critical for achieving the brand's signature texture, crispy on the outside, juicy on the inside. The sealed environment traps steam from the chicken's internal moisture, cooking it rapidly while locking in juices. The breaded pieces are loaded into metal baskets, which are then placed into the preheated pressure fryers filled with proprietary frying oil blends, typically high in stability and low in trans fats. Each fryer is pre-programmed to precise cooking parameters, controlling temperature and time based on the chicken type: bone-in, boneless, tenders, or wings. For original recipe bone-in chicken, the typical cooking cycle runs around 10 to 15 minutes at roughly 325 degrees under pressure. As the pressure builds, the internal temperature of the chicken rises quickly, reducing cook time while preserving moisture. Throughout the cooking process, sensors inside the fryer monitor oil temperature, pressure levels, and cooking duration, ensuring every batch turns out uniform and safe to eat. Once cooking is complete, the fry baskets are lifted automatically or by hand, and the chicken is allowed to drain for a brief period over the oil vat. Operators then transfer the finished product to a holding station, typically a heated cabinet or a moisture-controlled drawer that maintains the chicken at a safe temperature, usually above 140 degrees F, while preventing the crust from getting soggy. These holding cabinets are set to timers that ensure chicken is only kept for a limited time before it is discarded or rotated out, reinforcing KFC's strict freshness policy. Throughout this entire process, food safety is paramount. Every station is equipped with hand-washing sinks, sanitizer dispensers, and cleaning schedules that are enforced hourly. Employees wear gloves, aprons, and hairnets or caps, and facilities conduct routine microbial testing on surfaces and air to minimize contamination risks. Temperature logs, batch records, and fryer oil quality checks are performed regularly. The oil itself is filtered several times per day using built-in filtration systems that remove particulates and extend the oil's usable life while maintaining flavor quality. But the process doesn't begin or end in the kitchen. At the supply chain level, KFC relies on a cold chain network that keeps the chicken and ingredients at safe temperatures from the processing plant to the store. After the chicken is marinated and portioned at regional facilities, it is vacuum sealed or packed into airtight food-grade plastic bags, then stored in refrigerated trucks with active temperature tracking systems. GPS-enabled trailers ensure the logistics team can monitor both temperature and location in real time, avoiding spoilage or delays. The spice blends, breading flour, oil blends, and packaging materials are all shipped through similarly optimized networks, allowing stores to receive fresh inventory on a scheduled basis without interruption. When the chicken finally reaches the individual KFC restaurants, it is stored in walk-in coolers, prepped according to the exact procedures laid out by corporate training, and cooked fresh on-site throughout the day in small batches to keep up with demand. The entire system is designed for scalability and control, from a small store in a rural town to a flagship location in a major metropolis. The chicken tastes almost identical. That's the power of systematized food production at scale. Interestingly, much of KFC's fried chicken production still retains a manual, human-guided feel despite the high-tech systems that support it. While robotics and automation are increasingly common in many fast food chains, KFC's breading process continues to rely heavily on trained workers. This combination of human skill and industrial precision contributes to the unique texture and flavor of the final product. It all begins with the raw materials. At the core of the Big Mac are its two beef patties, 100% pure ground beef, with no fillers, additives, or preservatives. These patties are made from specially selected cuts of beef, typically chuck, round, and sirloin, all blended to achieve McDonald's specific fat-to-lean ratio, usually around 80-20. The cattle are sourced from approved ranches and farms, where animal welfare, feed quality, and traceability are tightly controlled. These suppliers operate under strict auditing and food safety programs to ensure consistency and safety throughout the entire supply chain. At the beef processing plants, the meat is first received in chilled form and stored in temperature-controlled environments. It then moves to large-scale grinders where the cuts are ground to a uniform consistency. The grinding process uses precision-engineered machinery that not only ensures even texture, but also mixes the fat content evenly throughout the meat. After grinding, the meat is portioned into exact patty sizes using high-speed forming equipment. Each Big Mac patty is a 1.6-ounce round that measures precisely to fit the 3-part sesame seed bun. Once the patties are formed, they are immediately flash frozen using cryogenic tunnels or spiral freezers. This locks in moisture and prevents microbial growth while maintaining the structural integrity of the patty. The frozen patties are then stacked into cartons, sealed, and loaded into refrigerated trucks that maintain a cold chain at all times. They are shipped to McDonald's distribution centers, which in turn supply local restaurants with scheduled deliveries to ensure freshness and efficient inventory management. But a Big Mac isn't just beef. Another critical component is the famous 3-part sesame seed bun: the crown, the club, and the heel. These buns are produced in large-scale commercial bakeries that specialize in McDonald's specifications. The dough is made from wheat flour, water, yeast, sugar, and conditioners to ensure softness and volume. The mixing and proofing process is closely monitored by computerized systems that control dough temperature and humidity. Once proofed, the dough is portioned into perfectly sized balls and dropped into custom baking molds designed specifically for the Big Mac's 3-part structure. The top bun is topped with sesame seeds just before baking. Conveyor ovens bake the buns at precisely calibrated temperatures for consistent color, texture, and internal moisture. After baking, buns are cooled on spiral cooling racks, then sliced, and the 3 segments are separated and packaged accordingly. Like the patties, the buns are then flash frozen or refrigerated and shipped to McDonald's outlets. Another defining component of the Big Mac is its sauces and toppings, specifically the Big Mac Special Sauce. The exact formula is proprietary, but the flavor is unmistakable. A tangy, creamy, slightly sweet sauce that combines elements of mayonnaise, mustard, relish, garlic, onion powder, and other spices. This sauce is manufactured in centralized condiment processing facilities, where ingredients are blended in large stainless steel tanks using industrial mixers that maintain a homogeneous emulsion. The final product is pumped into sealed, portion-controlled containers that are shipped cold to restaurants. In addition to the sauce, there are sliced pickles, dehydrated onions that are rehydrated on-site, shredded iceberg lettuce, and American cheese. The pickles are cut from whole cucumbers and brined in tanks with a proprietary vinegar and spice solution. They're sliced to a uniform thickness, then packed in brine to retain crunch and flavor. The onions come pre-chopped and dehydrated to extend shelf life and reduce spoilage. They are soaked in cold water at the store level before use. Lettuce is shredded in controlled processing plants and packed into vacuum-sealed bags. It must meet specific dimensions for length and width to ensure even coverage and manageable volume in the sandwich. The cheese, a processed slice tailored for meltability and flavor stability, is individually wrapped and delivered refrigerated. At the restaurant level, the Big Mac is assembled in a precise, time-tested sequence designed for speed and uniformity. When a customer places an order, the kitchen system relays it to the grill and assembly line. The patties are cooked on a dual-sided clamshell grill, a piece of kitchen equipment that cooks both sides of the patty simultaneously. This reduces cook time to less than a minute, while ensuring the internal temperature reaches the USDA required safe zone of 155 degrees Fahrenheit or higher. The grills are calibrated multiple times a day to maintain consistent heat, and they include timers and temperature sensors that alert the crew when patties are done. Simultaneously, the buns are toasted on a vertical conveyor toaster that crisps the inside surfaces while leaving the exterior soft. Each bun, top, middle, and bottom, is inserted into a specific slot in the toaster, ensuring that they emerge in the correct sequence for stacking. The bun toaster is also calibrated for toast color and surface temperature, both of which affect the texture and structural integrity of the final sandwich. Once the patties and buns are ready, the assembly begins on a stainless steel prep table or station called the sandwich build line. Each component is added in exact order. The heel receives a half teaspoon of rehydrated onions, followed by shredded lettuce, 1 slice of cheese, and the first cooked beef patty. The middle bun is then placed on top, followed by a second layer of sauce, onions, lettuce, and pickles, then the second patty. Finally, the top bun is placed to crown the entire structure. Employees are trained to assemble the Big Mac with a high degree of consistency, using scoops and dispensers designed to deliver precise amounts of sauce, lettuce, and onions. Visual guides are often posted above the station, and training involves repetition to internalize the build order and portion sizes. Speed is crucial, but accuracy takes priority. Each Big Mac must be indistinguishable from the next. Once assembled, the sandwich is wrapped in specially designed cardboard clamshells or wrappers that help maintain heat without causing sogginess. These are placed in warming areas or immediately bagged for customer pickup, depending on the workflow of the kitchen. Each Big Mac is usually served within a 5 to 10 minute window of cooking, ensuring it is hot, fresh, and true to form. Food safety and quality assurance are embedded in every stage of this process. The patties are temperature checked with digital thermometers. Sauce containers are labeled with use by times. Lettuce and onions are discarded after a certain number of hours out of refrigeration. Crew members follow strict hygiene protocols, including hand washing every hour, wearing gloves, and rotating utensils to prevent cross-contamination. Regular audits and surprise inspections ensure compliance with these standards. McDonald's kitchens also operate with a high level of automation and integration. Point-of-sale systems are linked to kitchen monitors, which display order sequences in real time. Inventory systems track ingredient usage and automatically flag restocking needs. Even the toaster and grill equipment is connected to central management systems that log performance data, usage cycles, and maintenance schedules. Behind the scenes, logistics play a crucial role in Big Mac production. From farm to fryer, the ingredients move through a vast cold chain network supported by regional distribution centers. These hubs maintain constant temperature control and manage stock rotation to ensure that every restaurant has fresh, usable inventory. McDonald's works closely with third-party logistics companies and in-house supply teams to coordinate deliveries across thousands of outlets every day. Even sustainability is being integrated into the Big Mac's life cycle. McDonald's has committed to sourcing beef more responsibly, using packaging materials that are recyclable or compostable, and reducing waste in the supply chain. Many of the buns are baked in facilities that run on renewable energy, and fryers now use low-emission heating systems. The lettuce and pickles are sourced from farms that practice water conservation and integrated pest management. In the end, the Big Mac is more than a sandwich. It's a manifestation of precision food engineering on a global scale. What might seem like a simple fast food item is the result of decades of refinement in agriculture, logistics, processing, and food safety. The carefully orchestrated choreography of farmers, food scientists, line cooks, and engineers ensures that every customer experiences the same taste, texture, and satisfaction with every bite. Whether it's the sizzle of the patties on the grill or the final crown of the sesame bun, every step is designed to deliver that unmistakable Big Mac experience. It all starts with the dough. Domino's dough is made in regional commissaries, large-scale production facilities that supply fresh dough to stores several times a week. These commissaries receive shipments of high-quality wheat flour from trusted grain suppliers. The flour, typically enriched and with a mid-range protein content around 12%, is combined with water, yeast, salt, sugar, and a small amount of oil in massive stainless steel mixers. These mixers, with capacities ranging from hundreds to thousands of pounds, mix the dough until it reaches the desired elasticity and gluten development. The dough is then allowed to rest and rise in temperature and humidity-controlled proofing rooms. These chambers regulate fermentation precisely, letting the yeast activate and produce carbon dioxide, which is what gives the dough its airy structure. This stage is not rushed. Domino's prioritizes flavor and texture, allowing the dough to ferment for several hours or even overnight to develop deeper taste and a balanced chew. After proofing, the dough is portioned into individual balls using industrial dough dividers and rounders. Each ball is scaled for the correct pizza size: small, medium, large, or extra large, and placed into trays lightly coated with cornmeal or oil to prevent sticking. These trays are stacked into rolling racks and moved into refrigerated holding rooms. Chilled to slow further fermentation, the dough balls are now ready for transport. They're boxed, loaded into cold chain delivery trucks, and shipped to Domino's outlets across the region on a tightly managed delivery schedule. Now comes the tomato sauce, an essential component that gives every pepperoni pizza its acidic punch and signature flavor base. The sauce is made at centralized processing plants using vine-ripened tomatoes, typically harvested at peak season and steam-peeled for optimal flavor preservation. The tomatoes are ground and mixed with a proprietary blend of spices, including oregano, basil, garlic powder, onion powder, salt, and sometimes a pinch of sugar to balance acidity. This sauce is then pasteurized to ensure shelf stability and safety, and filled into sealed plastic pouches or buckets, which are shipped refrigerated to each Domino's location. Cheese, too, is a cornerstone ingredient in every pepperoni pizza. Domino's uses a special low-moisture, part-skim mozzarella blend developed for optimal melt, stretch, and browning. Large cheese manufacturing plants shred or dice the mozzarella into uniform pieces that fall easily onto the pizza and melt consistently. The cheese is bagged, nitrogen flushed to prevent spoilage, and stored cold until it's needed. Domino's has strict cheese specifications that regulate fat content, meltability, and even browning color curves during baking. And of course, there's the pepperoni. Domino's pepperoni is a type of cured, spiced sausage made from a mix of beef and pork. The meat is ground and blended with a spice mixture that includes paprika, garlic, crushed red pepper, fennel seed, and curing salts. After being emulsified, the mixture is stuffed into collagen casings and fermented to develop its tangy flavor profile. The pepperoni is then slow-dried, sometimes smoked, and aged until it reaches the correct firmness. Once matured, it's sliced into perfect, thin rounds that crisp slightly when baked, but but retain their juicy center. These slices are packed into refrigerated cases, typically with a layer of wax paper to prevent sticking, and distributed to stores for daily use. At the store level, the pizza making process begins when an order is received, either online, via app, or in-store. The store crew retrieves a dough ball from the walk-in cooler and places it on a prep table dusted with cornmeal or flour. Unlike hand-tossed pizzerias, Domino's uses a combination of manual and mechanical techniques to stretch dough. The dough ball is pressed using a dough press or roller to achieve the correct size and thickness. Then it may be hand-finished to achieve an even round shape with a defined edge, or cornicione. Once the crust is prepared, the pizza moves down the make line. A ladle of tomato sauce is spread in a spiral motion from the center outward, leaving a consistent border around the edge. Precision here is key. Too much sauce and the crust gets soggy. Too little and the pizza lacks flavor. Domino's uses portion-controlled utensils to ensure uniform application across thousands of pizzas a day. Next comes the cheese. Employees grab pre-measured amounts of shredded mozzarella from cold bins and scatter it evenly over the sauced crust, making sure to reach the edges to maximize melt and appearance. The cheese-to-sauce ratio is carefully designed to complement the crust thickness and baking conditions in the oven. Domino's often uses cheese guides or weight scales to prevent under or over application. Then it's time for the pepperoni, the star of the show. Domino's applies pepperoni in a uniform pattern, usually a ring-based layout that ensures each slice of the final pizza gets equal coverage. The pepperoni is placed on top of the cheese so it crisps and curls slightly during baking, creating those little greasy, flavorful cups that have become a hallmark of American pepperoni pizza. The number of pepperoni slices is not left to chance. Domino's has precise count targets per size, such as 30 slices for a medium and 40 for a large, ensuring every customer receives the expected experience. Once built, the raw pizza is placed onto a pizza screen or baking tray and sent into a conveyor oven. Domino's signature baking method. These ovens, called impinger ovens, are long, tunnel-like machines that use jets of superheated air to cook the pizza quickly and evenly. The oven belt moves at a fixed speed, typically cooking a pizza in about 6 to 7 minutes at a temperature of approximately 465 degrees Celsius to 500 degrees. The impingement cooking method forces hot air onto the top and bottom surfaces of the pizza simultaneously, ensuring a crisp crust and melted, browned cheese with consistent results. As the pizza exits the oven, crew members perform a quick visual check for doneness. The cheese should be fully melted and bubbling, the pepperoni slightly curled with crispy edges, and the crust golden brown. The baked pizza is transferred to a cutting board and sliced with a rolling blade into even segments, typically 8 for a large pizza. The blade is wiped between uses to prevent sauce and cheese buildup. The pizza is then placed into a specially designed Domino's pizza box made from recycled corrugated cardboard. These boxes are ventilated to allow excess steam to escape, preventing sogginess during delivery. Each box is folded and branded with Domino's blue and red logo and has space for order stickers, promotional labels, and QR codes. A thermal lining or pizza insert may also be used in some regions to help retain heat during transport. Once boxed, the pizza is either handed over to a customer in-store or placed into an insulated delivery bag. These bags are engineered to retain heat and allow limited airflow, keeping the pizza hot but not steamy. Domino's delivery drivers follow optimized GPS routes generated by proprietary software that prioritizes speed and traffic conditions. Many stores use heat racks or warming stations to hold pizzas briefly while waiting for drivers or curbside pickup. Behind the scenes, Domino's uses sophisticated technology to monitor every step. The point-of-sale system automatically tracks inventory levels. Real-time analytics inform store managers about the number of pizzas being ordered, the time each step takes, and potential bottlenecks. Domino's Pizza Tracker gives customers live updates on the progress of their order, from prep to baking to out for delivery, driven by timestamps and kitchen inputs. Cleanliness and food safety are integral to every stage. Dough trays and utensils are washed in commercial dish machines between uses. Gloves are worn and changed frequently. Prep stations are sanitized regularly throughout the day. All cold ingredients are stored in reach-in coolers with thermometers to maintain optimal temperature. Internal audits and third-party inspections ensure compliance with food safety standards and corporate procedures. To craft Starburst, factories begin with a foundation of raw materials, with the primary ingredients being sugar, corn syrup, hydrogenated palm kernel oil, fruit juice concentrates, citric acid, and natural and artificial flavors. Food-grade colorants such as Red 40, Yellow 5, and Blue 1 give the candy its vibrant, recognizable hues. Sugar, the dominant ingredient, is typically sourced from sugar beets or sugar cane, refined to a fine, white granulated form. Corn syrup, essential for achieving the chewy consistency, is extracted from dent corn and then enzymatically converted into glucose-heavy syrup. This syrup not only sweetens, but also inhibits crystallization, allowing for the distinctive, flexible Starburst chew. Fruit juice concentrates are selected based on seasonal availability and flavor profiles, often involving apple, cherry, orange, strawberry, lemon, and other citrus bases. Each concentrate is filtered and reduced under vacuum conditions to intensify the flavor while removing excess water. Meanwhile, citric acid, either derived from citrus fruits or biosynthesized using Aspergillus niger fermentation, is added to sharpen the tart notes and stabilize the pH level. Palm kernel oil, after undergoing hydrogenation to solidify its structure, contributes to the smooth mouthfeel, acting as a lubricant and textural agent within the candy matrix. All of these ingredients are delivered to the factory in bulk. Sugar and corn syrup via silo systems and tanker trucks. Oils in heated storage tanks. And flavoring agents in sealed food-grade containers to maintain freshness and prevent contamination. Once inside the facility, the first major step in the Starburst making process is ingredient weighing and batching. Massive computerized batching systems measure exact quantities of each component using load cells and automated valve controls. Sugar and corn syrup are combined in stainless steel jacketed mixing tanks where they are preheated to around 115 degrees Celsius. This begins the process of dissolving the sugar crystals into a homogeneous syrup base. Agitators inside the tanks ensure uniformity and prevent scorching. The heated syrup is then transferred to a vacuum cooker. In the vacuum cooking chamber, the syrup is exposed to reduced atmospheric pressure, allowing water to evaporate at a lower temperature. This technique is critical in candy making, as it prevents the sugar from caramelizing or breaking down under intense heat. As moisture is removed, the syrup thickens into a viscous mass with a specific Brix value, typically between 85 and 90% solids content, ensuring it will solidify into a chewy form once cooled. The exact cooking time and temperature are closely monitored via sensors and control systems linked to the plant's supervisory control and data acquisition platform, or SCADA. After cooking, the thickened candy mass is transferred through heated conduits into a mixing chamber known as a color and flavor cooker, or kneader. Here, hydrogenated palm kernel oil is added to help emulsify the mixture and control the final texture. Food-safe mixing blades, often paddle style or Z-blade types, churn the mass at controlled speeds. This is also the point where colorants, acids, and flavor concentrates are injected. High-precision peristaltic pumps ensure accurate dosing of color and flavor to maintain batch consistency, and the mixer is divided into multiple compartments if producing more than one flavor at a time. For instance, strawberry might be mixed in one chamber, lemon in another, and cherry in a third. Each batch customized with different concentrations of fruit essence and specific pH levels for optimal taste balance. Once the flavor-specific masses are ready, They must be cooled to a workable temperature, typically around 60 degrees Celsius, before shaping. Cooling belts equipped with air curtains and stainless steel rollers gently lower the temperature without causing hardening or premature setting. From here, the candy mass is directed into the forming line, a highly orchestrated system of extrusion, cutting, and wrapping. Extrusion is the next key phase. Using positive displacement gear pumps or auger-driven extruders, the warm candy mass is pushed through stainless steel nozzles with rectangular cross-sections. This creates long, continuous ropes of candy with a consistent width and height, matching the final Starburst dimensions. Servo motors carefully control the extrusion speed to synchronize with the downstream cutting process. If multiple colors or flavors are being co-extruded, special twin-screw extruders equipped with internal baffles can combine two masses into a single, dual-colored strand, which adds visual interest and flavor complexity. The ropes move onto a conveyor equipped with cooled rollers to maintain their shape. A high-speed guillotine cutter controlled by an optical sensor system slices the rope into individual blocks with precise timing. The cutting knives are made from food-grade stainless steel and are lubricated with a microfine spray of food-grade oil to prevent sticking. Each candy piece is now in its iconic rectangular shape, ready for wrapping. Wrapping Starburst is a marvel of mechanical ingenuity. Each piece must be individually wrapped in waxed paper to preserve freshness and prevent sticking. Automatic folding and wrapping machines, operating at speeds of up to 800 pieces per minute, perform this delicate operation with stunning precision. These machines use synchronized mechanical arms to position each candy, fold the wax paper around it using rotary folding drums, and seal it using gentle pressure rather than heat, which might soften the product. The wrapped pieces are then collated by vibratory feeders and assembled into 4-piece packs in various flavor assortments. These grouped candies are fed into a horizontal flow wrapper, where they are encased in the familiar branded packaging film. The flow wrapper uses a combination of rollers, film unwinders, photo eye sensors for alignment, and end-sealed jaws to create hermetically sealed packages that protect the candy from moisture and oxygen. The film is often reverse printed with branding, nutritional information, and batch tracking codes. Nitrogen flushing may be used in some production lines to displace oxygen and extend shelf life. After packaging, each unit passes through metal detectors and X-ray scanners to ensure there are no foreign objects or contaminants. Vision inspection systems verify print clarity, package seal integrity, and correct product count. Random samples are pooled for manual inspection by quality control technicians who assess texture, flavor, intensity, size, and appearance. Finished goods are then loaded into cartons by robotic case packers and labeled with lot codes for traceability. These cartons are palletized by robotic arms equipped with vacuum grippers, stacked in strategic configurations to optimize warehouse space and prevent crushing during transport. Once pallets are complete, they are shrink-wrapped and transferred via automated guided vehicles to temperature-controlled storage areas. Though Starburst is shelf-stable, storing it in a cool, dry environment prevents oil separation, flavor degradation, and textural hardening. From these warehouses, Starburst products are shipped out via freight trucks or distribution centers, eventually reaching retail shelves in supermarkets, vending machines, and convenience stores around the world. What makes the Starburst manufacturing process particularly interesting is the interplay between artistry and automation. While the ingredients themselves are simple, achieving the exact chewiness, vibrant color, and flavor burst that consumers expect requires precision-engineered machinery, tight process control, and an unyielding commitment to consistency. The smallest variation in moisture content, mixing speed, or cutting pressure could result in a piece that's too hard, too sticky, or aesthetically flawed. Despite being a candy rooted in simplicity, the industrial complexity behind Starburst underscores the broader evolution of confectionery manufacturing. Today's production lines incorporate real-time analytics, inline spectroscopy for flavor consistency, and even machine learning algorithms that predict equipment maintenance needs to avoid downtime. Some newer factories are experimenting with plant-based colorants and sustainable packaging materials, aiming to meet consumer demand without compromising on quality. There's even ongoing research into using recycled steam and closed-loop water systems to reduce the environmental footprint of candy production lines like those making Starburst. Mentos were first created in the early 20th century and gained global popularity due to their unique texture and intense flavor. The combination of a crunchy outer coating and a chewy interior is what sets them apart, and achieving that contrast requires precise formulation and processing. The base recipe revolves around sugar, glucose syrup, hydrogenated coconut or palm kernel oil, gelling agents like gelatin or modified starches, natural and artificial flavors, food-grade colorants, and glazing agents such as carnauba wax. Depending on the variety, mint, fruit, cola, or sour, the flavoring system will differ, but the core production mechanics remain largely the same. Production begins with the sourcing and handling of raw ingredients. Sugar is delivered in bulk form, typically refined cane or beet sugar, and stored in large silos within the factory. Glucose syrup, derived from enzymatically treated cornstarch, arrives in insulated tanker trucks and is stored in jacketed holding tanks to keep it fluid and at the proper viscosity. Oils are stored in temperature-controlled containers to maintain consistency. Each of these raw materials is subjected to a series of pre-checks. Sugar is tested for grain size and moisture content, glucose syrup for dextrose equivalent values, and oils for peroxide levels and stability. The factory's quality control department samples all incoming ingredients and verifies their compliance with specifications using chromatography, spectroscopy, and other chemical assays. Once approved, the first step in making Mentos centers on the formation of the candy core. Unlike many confectionery items, the chewy center of a Mentos is not extruded or cast, but formed using a process called compression or tableting. But before compression can occur, a slurry is created by blending sugar, glucose syrup, and oils in large mixing kettles equipped with paddle agitators. This mixture is partially cooked to evaporate water and develop the candy's elasticity. Once it reaches the desired consistency, typically with a Brix reading of about 85% solids, it is transferred to a cooling table where it is kneaded to achieve the ideal texture. The cooled mass is then broken into chunks and fed into a granulator, which reduces it into fine, uniform particles suitable for compression. These particles are sieved to ensure consistent particle size, which is critical for proper tablet formation. A binding agent, often modified starch or gelatin powder, is then added to help the particles fuse during compression. The powdered base is then fed into rotary tablet presses, high-speed machines equipped with stainless steel dies and punches that compress the powder into uniform cylinders. Each tablet is subjected to high compression force to achieve the dense, elastic core that is characteristic of Mentos. These presses can produce thousands of tablets per minute, and they feature real-time monitoring systems to ensure weight, hardness, and thickness are within specifications. The freshly compressed tablets are soft and not yet glossy. At this stage, they are known as centers and will undergo further processing to become the finished product. These centers are now ready for the panning stage, a method of coating used to apply multiple layers of sugar and flavor to build up the candy shell. The panning process takes place in large, rotating stainless steel drums called coating pans or Drageses pans. The cores are loaded into the pan, which rotates at a controlled speed while fine sprays of syrup, flavor, and color are applied in successive passes. Initially, a syrup consisting of dissolved sugar and glucose is sprayed onto the tablets using atomizing nozzles. Hot, dry air is simultaneously blown into the pan via air ducts, which rapidly evaporates moisture and causes the sugar to crystallize onto the surface of the tablets. This process is repeated over and over, sometimes more than 30 times per batch, to gradually build up the characteristic crunchy coating of Mentos. During these cycles, food-grade colorants and additional flavoring agents are also introduced. Different panning cycles are used for mint and fruit flavors. For example, mint Mentos typically receive a higher concentration of menthol and peppermint oil in the outer layers, while fruit Mentos require individualized flavor additions like strawberry, orange, and lemon, each blended with acidulants such as citric or malic acid to amplify the taste. Achieving uniform coating thickness, color distribution, and surface smoothness requires expert control of several variables: syrup viscosity, pan speed, airflow rate, and ambient humidity. Most modern Mentos facilities use programmable logic controllers and environmental monitoring systems to automate these parameters and ensure repeatability across batches. The entire panning process can take several hours, as each layer must dry before the next is applied. Operators use inline sensors and visual inspections to check for surface integrity, ensuring that no rough spots or cracks appear as the coating thickens. Once the desired shell thickness is achieved, the tablets undergo a drying and stabilization phase in climate-controlled holding rooms. Here, they rest for several hours, allowing residual moisture to equalize and the structure to firm up. The next step is polishing, a critical final touch that gives Mentos their trademark shine and smooth finish. Tablets are reloaded into specialized polishing pans and treated with a mixture of glazing agents such as carnauba wax and microcrystalline wax dissolved in ethanol or isopropyl alcohol. As the pan rotates, the wax mixture is sprayed lightly onto the surface of the tablets and then buffed by friction as the candies tumble against one another. This step not only enhances visual appeal, but also serves a functional role, creating a moisture-resistant barrier that extends shelf life. After polishing, the finished candies are cooled again to harden the glaze and prevent sticking. They are then conveyed to the packaging area via vibratory conveyors and sorting belts that align them into consistent orientations for loading. Modern Mentos factories use high-speed flow wrapping machines capable of packaging dozens of rolls per minute. The individual candies are fed into paper or plastic film wrappers, which are then heat-sealed and crimped into the familiar cylindrical Mentos roll. These rolls are typically grouped into multi-packs or display trays using robotic case packers and then passed through labeling stations where batch codes and expiration dates are applied using inkjet or laser printing systems. To ensure food safety and quality, each roll passes through a series of automated inspection stations. X-ray machines and metal detectors scan for foreign objects, while vision systems inspect label placement, roll integrity, and seal quality. Statistical quality control sampling is performed by trained technicians who manually test rolls for chewiness, coating hardness, gloss level, and flavor profile using a standardized scoring system. Any deviations trigger a hold on the batch and a review of equipment calibration and ingredient records to pinpoint the source of variation. Pallets of Mentos rolls are finally shrink-wrapped and transferred to the factory's finished goods warehouse, where they are stored under tightly controlled temperature and humidity conditions. Though Mentos are relatively shelf-stable, proper storage conditions ensure they retain optimal flavor, texture, and appearance for months. From there, the products are distributed through regional logistics hubs to retail outlets around the globe. While consumers might simply pop a Mentos into their mouth without much thought, The reality is that each piece embodies a tremendous amount of behind-the-scenes engineering. From the uniform density of the core to the microscopic layering of sugar shell, every step in the process is fine-tuned to ensure consistency at massive production scales. Advanced data analytics platforms are increasingly being used in Mentos factories to track machine performance, ingredient variation, and environmental fluctuations, helping operators predict and prevent quality issues before they occur. The candy's production is also seeing innovations aimed at sustainability, including the use of biodegradable wrappers, energy-efficient panning systems, and closed-loop water recycling technologies. Some manufacturers are exploring plant-based gelling agents to create vegan-friendly versions of the product, expanding the Mentos appeal to a broader market while keeping the signature experience intact. The story of Skittles production begins with the sourcing of raw ingredients. The core of each Skittle consists primarily of sugar, corn syrup, and hydrogenated palm kernel oil, combined with fruit juice concentrate, citric acid, natural and artificial flavors, and gelatin or a plant-based gelling agent, depending on the variety. Food colorants such as Red 40, Yellow 5, Blue 1, and others provide the vivid, rainbow-like appearance, while carnauba wax is used for the final shine. All ingredients arrive at the factory in bulk, sugar in pneumatic tankers or super sacks, corn syrup in heated tank trucks, oils in insulated totes, and flavors and colors in sealed drums to preserve potency and prevent contamination. Once the raw materials are delivered to the facility, they undergo quality inspection. Sugar is tested for purity and grain size using optical sensors and moisture analyzers, while corn syrup is evaluated for its dextrose equivalent to ensure consistent sweetness and viscosity. The oils are checked for oxidative stability and melting point, and flavor compounds are tested with chromatography to confirm identity and strength. Approved ingredients are then routed to ingredient storage silos or intermediate tanks, each connected via stainless steel piping to the central mixing systems. The production of Skittles begins with the creation of the chewy center, which is not molded or extruded like many other candies, but rather formed through a process known as casting or deposition. First, sugar, corn syrup, and oils are combined in large, stainless steel, steam-jacketed kettles. Agitators mix the contents while the batch is heated to around 115 to 120 degrees Celsius. This heating step is critical. It dissolves the sugar, reduces viscosity, and activates the gelling agents that will give the Skittle its characteristic chewy texture. Once the mixture reaches the desired consistency, it is partially vacuum cooked to remove excess moisture, yielding a thick, elastic syrup. This candy mass is then deposited into starch molds, which are preformed trays filled with cornstarch that contains indentations for each candy. Depositing heads, essentially nozzles controlled by servo-driven pumps, release precisely metered amounts of the syrup into each cavity. These molds are then transferred via conveyor into a climate-controlled drying tunnel where they remain for 24 to 48 hours. During this time, water evaporates slowly and uniformly, and the chewy texture begins to set. After drying, the starch is separated from the candy cores using a destarching system. This equipment gently shakes and brushes off the remaining starch, which is collected, filtered, and reused in future cycles. The now formed Skittle centers are tumbled in large rotating drums to smooth their surface before being passed to the next critical step, the sugar shell coating, also known as panning. Panning is a cornerstone of Skittles production and one of the most technically demanding phases of the process. The centers are placed into enormous rotating pans, typically several meters in diameter, where the sugar coating is built up through dozens of thin layers. Each pan spins continuously, and while it does, a fine sugar solution is sprayed onto the candy centers. This syrup typically consists of refined sugar, glucose, water, and sometimes citric acid for tartness. Immediately after spraying, a blast of temperature and humidity-controlled air is directed into the pan, drying the surface and forming a thin, hard layer. This coating process is repeated many times, sometimes for several hours, depending on the desired shell thickness. Different flavor syrups are added at different stages if multiple fruit profiles are being used within the batch. The rotation speed, spray volume, airflow rate, and drying temperature are all managed by PLC-controlled systems that monitor pan performance in real time, ensuring consistency in shell formation. Operators oversee the process via touchscreen HMIs, adjusting parameters based on real-time data and sensory feedback from test samples. Once the shell has reached its final thickness, color is added. This is typically done with 1 or 2 additional layers of tinted sugar solution, each one custom formulated for a specific flavor variant. Red for strawberry, yellow for lemon, green for lime or apple, purple for grape, and orange for naturally orange. These solutions include FDA-approved food dyes, stabilized with acidulants and emulsifiers to ensure even distribution and adhesion to the candy surface. The result is a batch of candies, each uniformly colored, with a bright and durable outer shell. Next comes the finishing stage, where Skittles are given their unmistakable gloss. This is achieved using polishing pans and a mixture of carnauba wax and microcrystalline wax, sometimes diluted in alcohol to aid dispersion. The candies are tumbled gently while a fine mist of the wax solution is sprayed onto them. As the pan rotates, the candies polish each other through friction, creating a smooth, shiny finish. This step also provides a moisture barrier that helps extend shelf life and prevents the candies from sticking together in the package. After polishing, the Skittles are passed through cooling tunnels to solidify the coating and stabilize the structure. Then comes the critical stage of flavor sorting and portioning. High-speed sorting machines equipped with optical sensors separate the candies by color, using burst air jets to redirect them into designated channels. This ensures that each bag or pack of Skittles contains the full assortment of flavors in consistent proportions. The sorted Skittles are then conveyed to packaging stations, where they are portioned using volumetric or weight-based fillers. Each batch is dispensed into the appropriate packaging format, whether single-serve pouches, resealable share bags, or rigid tubes. The packaging film is reverse printed with branding, nutritional information, and traceability codes, and it is fed into horizontal or vertical form-fill seal machines. These machines form the pouches, fill them with product, and seal them in one continuous motion. Precise temperature and pressure controls ensure that the seals are airtight without melting the product inside. As the packaged Skittles exit the line, they are subjected to a series of inspection checkpoints. Metal detectors, X-ray systems, and vision scanners verify that each package contains the correct amount, is sealed properly, and is free of contamination. Random samples are pulled for quality testing, evaluating chewiness, shell thickness, flavor strength, and visual appearance. Some factories even use texture analyzers and sensory panels to verify that the candies meet brand specifications. Once approved, the packages are collated into cartons using robotic case packers and then palletized by automated stacking systems. Each pallet is stretch wrapped for stability and labeled with tracking information, including production time, line number, and batch code. Pallets are then routed to the warehouse, where they are stored in temperature and humidity controlled conditions to maintain optimal product integrity. Skittles are remarkably shelf stable, but proper storage conditions ensure that the texture remains soft and the colors do not fade. From the warehouse, Skittles are distributed via truck to retail distribution centers, grocery stores, vending machines, and online fulfillment facilities. The journey from raw ingredients to store shelves is timed to ensure freshness and consistency, with sophisticated supply chain software tracking every shipment to maintain inventory and respond to fluctuations in demand. The production of Skittles is not only an example of precision manufacturing, but also one of mass customization. Despite being produced in colossal quantities, every single piece must conform to strict standards of flavor, size, color, and texture. Innovations in data analytics, predictive maintenance, and machine learning are being introduced into Skittles factories to continuously improve yield, efficiency, and sustainability. Energy-efficient drying systems, water reclamation units, and biodegradable packaging research are helping the brand minimize its environmental impact without compromising the product's appeal. It all begins long before a Dunkin' Donut ever meets a customer's lips. The journey of a factory-made Dunkin' Donut starts in massive industrial facilities engineered specifically for high-throughput baking and frying. Unlike the fresh, hand-prepared donuts in local bakeries, the factory-produced donuts that supply regional distribution centers or large retail outlets are the result of a tightly choreographed sequence of automated, mechanized operations, each designed to maximize consistency, food safety, and output volume. The core ingredients of a Dunkin' Donut seem simple: wheat flour, sugar, yeast or chemical leavening agents, eggs or egg solids, milk derivatives, oil, and water. But each of these components must meet stringent specifications. The wheat flour is typically sourced from large milling operations and arrives at the factory in bulk pneumatic tankers. Once offloaded into giant silos, it's carefully monitored for protein content, moisture, and particle size. These parameters are crucial as they directly affect gluten development, dough elasticity, and fry stability. The sugar, often in fine granulated form, is similarly delivered in bulk and stored in temperature-controlled hoppers to prevent clumping. The yeast, which may be active dry or instant, is carefully handled to maintain viability. For cake-style donuts, chemical leaveners such as sodium acid pyrophosphate and baking soda replace yeast, requiring exact dosages to control rise, texture, and batter pH. Liquid ingredients like water and milk concentrates are pumped from stainless steel reservoirs through filtered lines. Egg solids, whether powdered or liquid, are introduced via sealed containers to reduce contamination risk. At the heart of the process is the dough preparation system. In a typical yeast-raised donut line, a computerized batching system automatically dispenses pre-weighed quantities of dry and wet ingredients into a horizontal spiral mixer, usually a high-capacity unit capable of mixing several hundred pounds per batch. This mixer blends the ingredients through a timed, multi-speed cycle, a slow initial mix to hydrate the flour, followed by a high-speed kneading phase to develop the dough's structure. Temperature probes ensure the dough reaches the optimal final mix temperature, often around 78 to 82 degrees. Any deviation can alter fermentation speed and finished product quality. Once mixed, the dough is transferred, either manually in smaller setups or via automated dough elevators in large-scale operations, to intermediate proofing cabinets. These are large chambers that maintain a warm, humid environment, typically around 90 degrees Celsius, with 85% humidity. The dough rests here for 30 to 45 minutes, allowing initial yeast fermentation to begin. This resting period improves extensibility and relaxes the dough for sheeting. From the proofing cabinet, the dough moves to the sheeting line. Here, massive rollers flatten the dough to a precise thickness, often controlled by laser-guided sensors. A conveyor belt feeds the dough through a series of increasingly fine rollers, each pressing it thinner until it reaches the exact gauge required for donut formation. Dusting flour is automatically sprinkled to prevent sticking, and scrap management systems collect unused dough trimmings to be reprocessed in future batches. Next, the formed dough sheet moves to the rotary cutter station. This is where the signature donut shapes come to life. Custom-designed rotary dies stamp out rings, holes, or specialty shapes like filled bars or seasonal themes. Each cutter is precision machined to minimize dough stress, ensuring even fry results. A vacuum system gently lifts and removes cut donuts from the scrap dough matrix, depositing them onto another conveyor in perfect alignment. These unbaked, shaped donuts are then transferred to the final proofer, a massive multi-tiered system that can resemble a vertical carousel. Moving slowly through this enclosed environment, the donuts are proofed for anywhere from 35 to 60 minutes, depending on product type and yeast activity. This is a critical phase. The dough expands, air cells develop, and the signature light texture of a yeast donut forms. Relative humidity and temperature are tightly regulated to promote even rising. Once proofed, the donuts enter the fryer. This is one of the most visually captivating moments in the factory. Rows upon rows of pale, risen dough transforming into golden brown perfection. Industrial donut fryers are long, shallow troughs filled with high-stability frying oil, typically a blend of soybean or palm oil designed to withstand high temperatures without breaking down. The donuts enter via an automated conveyor that gently lowers them onto the surface of the hot oil, held between 350 to 375 degrees. Floating racks or submerged mesh baskets keep the donuts evenly spaced and ensure uniform frying on both sides. The donuts are flipped halfway through using automated paddles or turning bars, so each side receives equal exposure. Fry time is typically 90 to 120 seconds per side for yeast-raised varieties. Throughout the fryer, oil filtration and replenishment systems remove debris and maintain oil quality, critical for flavor, texture, and food safety. After frying, the donuts move onto a draining belt where excess oil is wicked away using absorbent conveyor surfaces or air knives. From there, they transfer directly to a cooling tunnel, an enclosed, climate-controlled conveyor that gently brings the donuts down to ambient temperature. This cooling phase, usually lasting 8 to 12 minutes, stabilizes the structure and prevents condensation before glazing or filling. Now comes one of the most iconic steps: glazing. The donuts pass beneath a cascading curtain of warm glaze, typically made of powdered sugar, water, and stabilizers like corn syrup or mono and diglycerides to ensure sheen and viscosity. The glaze is held at precise temperatures, around 105-115 degrees Fahrenheit, to allow smooth coating without excessive dripping. Any glaze runoff is collected, filtered, and reused within quality limits. For filled donuts, a separate line handles injection. This is a precise, high-speed process where each donut is clamped and filled through nozzles that inject jelly, cream, custard, or other fillings. Volumetric pumps control exact fill amounts, typically between 15 to 25 grams per donut, to ensure uniformity. The timing of this step depends on whether the donut is glazed before or after filling, a decision made based on the type of coating or desired product appearance. Topped donuts, such as Boston cream or chocolate frosted, pass through enrobing units or individual depositor stations. These machines spread or pipe icing onto the surface, using rotating drums or mechanical arms to achieve even distribution. Sprinkles, nuts, or other toppings may be applied via shaker systems or robotic garnishing heads, with vacuum sensors ensuring no foreign objects are introduced. Once coated, the donuts continue on conveyors to the packaging area. Here, an optical vision system inspects each unit for shape, color, topping placement, and fill integrity. Defective products are automatically rejected and diverted for analysis or disposal. The acceptable donuts proceed into robotic tray loaders or auto packing machines. For bulk shipments, donuts may be arranged in plastic trays stacked into crates. For retail packs, form-fill seal systems wrap donuts in individual or multi-unit blister packs using heat-sealed film. Each packaged unit receives a date code and product identifier via inkjet printer or laser etching. Metal detectors and X-ray scanners stand guard just before final packaging to catch any foreign materials, from metal fragments to hard plastics. At this point, the product has passed through over a dozen safety checks, far more rigorous than what a local bakery could feasibly achieve. Before leaving the factory, pallets of donuts are weighed, logged, and tagged with RFID labels for inventory tracking. They're stored in temperature-controlled staging areas until trucks arrive. Distribution fleets, often operated by third-party logistics firms, are designed to transport the donuts quickly to regional warehouses or direct-to-store delivery networks. Because many factory-made donuts are frozen for extended shelf life, refrigerated trucks or freezer compartments maintain ideal storage conditions throughout transit. Once at a distribution center or store, the donuts are thawed if necessary and either resold in packaged form or used to stock fresh counters in Dunkin' outlets. Some outlets may perform final finishing touches, like adding fresh glaze, sugar dusting, or customized toppings. But the bulk of the preparation has already occurred at the factory, where industrial consistency reigns supreme. Before a Subway sandwich ever reaches the customer's hands, its journey begins far from the store counter, in sprawling, high-efficiency food manufacturing plants that are responsible for producers with capacities reaching up to 1,000 pounds per batch, perform a sequence of low-speed and high-speed kneading to develop the gluten network necessary for Subway's springy, chewy bread texture. Temperature-controlled water and chilled mixing bowls help maintain the dough temperature, typically around 78 degrees Celsius, essential for proper fermentation. After mixing, the dough is unloaded onto transfer belts and sent into a first-stage resting tunnel or intermediate proofer. Here, the dough rests in a humid, warm environment to allow the yeast to activate and create carbon dioxide, giving the dough extensibility before shaping. Next, the dough is portioned using volumetric dividers that slice the mass into uniform weights. These pieces then pass through rounding and molding machines that elongate them into the familiar Subway sandwich roll shape. Automated flour dusters and non-stick belts ensure smooth passage through the shaping process. For breads with toppings like oats or cheese, the dough passes under a rolling applicator or static sprinkler before entering the next proofing stage. The proofing phase is critical. Dough pieces are placed onto pans and loaded into an industrial proofer, a large, climate-controlled chamber with tiered racks or chain-driven carriers. Inside, the bread rises for 45 to 60 minutes at around 90 degrees Celsius with high humidity. Dough height, elasticity, and fermentation rate are monitored using sensors or inline imaging to guarantee uniform rise. Once proofed, the dough pans move into the par baking ovens. These are tunnel or rack ovens heated to approximately 420 degrees. The bread bakes for about 8 to 10 minutes, enough to set the structure and crust, while preserving enough internal moisture so it can be finished baking in store. After baking, the loaves are cooled in ambient air tunnels before being packaged. Packaging is a delicate process. The cooled loaves are inserted into specially ventilated film or bulk freezer trays. Modified atmosphere packaging may be used to extend shelf life and prevent freezer burn. All packaging is date-coded, labeled with batch tracking, and sent through metal detectors or X-ray systems. Then the bread is quickly frozen in blast freezers that bring core temperatures below zero in under 90 minutes, preserving quality for shipment. While the bread is handled this way, meat and poultry ingredients follow a parallel but very different industrial route. Subway's deli-style meats, turkey breast, ham, roast beef, and chicken strips are cooked, sliced, or formed in specialized meat processing plants. These facilities receive USDA-inspected raw proteins that are boned, trimmed, and cleaned under strict sanitary guidelines. The raw meats are portioned, tumbled, and marinated with Subway's proprietary brine formulas, which often include salt, phosphates, sugar, and flavorings. In the case of chicken strips or patties, the meat may be fully cooked in steam ovens or grill presses, then flash frozen to lock in moisture. Roast beef and turkey, on the other hand, are typically cooked in steam ovens or combi ovens that simulate traditional roasting while maintaining high throughput. Once cooked, the meats are cooled using spiral chillers or glycol plate systems, then sliced on high-speed rotary slicers for uniform thickness. These slices are stacked and portioned by weight using automated weighing machines, then sealed in vacuum pouches or controlled atmosphere trays. Each portion is sealed with batch coating and passed through inspection systems before being packed into cartons and frozen for distribution. Cheese slices, Swiss, American, provolone, and pepper jack, are produced using high-speed forming and slicing systems. Cheese blocks are first melted down, then reformed into large sheets which pass through slicing blades and portion conveyors. Anti-stick sheets are often placed between slices, and stackers organize the cheese into count-specific bundles, each packaged under vacuum or gas-flushed atmospheres to preserve shelf life and prevent molding. Vegetables such as lettuce, tomatoes, cucumbers, onions, and green peppers are not grown in factories, but they do undergo industrial preparation before arriving at each store. Lettuce, for example, is harvested, washed with chlorinated or ozonated water, and shredded in high-speed slices. Tomatoes are cleaned, visually inspected, and machine sliced before being layered between food-safe pads that prevent bruising during shipping. Onions are peeled, sliced, and packaged in gas-flushed bags to reduce spoilage and preserve freshness. All vegetables are packed in refrigerated, ready-to-use formats and delivered through cold chain logistics to ensure they remain crisp and safe for consumption. Subway's specifications for produce are among the most rigorous in the QSR industry, often requiring vendors to perform multiple microbial tests before product release. Sauces, ranch, Chipotle Southwest, mayonnaise, mustard, sweet onion, and many others are made in liquid processing plants that function much like beverage or dairy factories. These facilities handle emulsion preparation in large mixing tanks fitted with high shear homogenizers. Ingredients like oils, water, spices, thickeners, and preservatives are blended under vacuum to ensure air-free, stable emulsions. The sauces are then pumped into sterile filling machines that dispense measured volumes into squeeze bottles, bulk pouches, or portion cups. Heat sealing, tamper-evident caps, and nitrogen flushing preserve shelf life. Every component, from bread to sauce, is designed with logistics and final assembly in mind. Once all the parts are complete, they're loaded onto pallets, sorted into refrigerated and frozen shipments, and transported to Subway's distribution centers. From there, truck routes are carefully scheduled to ensure timely delivery to thousands of store locations. All products are scanned, tracked, and recorded during shipment, ensuring cold chain integrity and traceability from plant to sandwich counter. Inside the store, the staff becomes the final assembly line. Each morning, the frozen bread dough is thawed and given a second proof before finishing its bake in the store's convection ovens. Meats are defrosted and held in refrigerated bins, vegetables are placed into prep trays, and sauces are opened and loaded into squeeze bottles. Sandwich artists follow precise build sheets and portioning guides to ensure a consistent experience for the customer. Even at the store level, there are echoes of the factory's precision. How many ounces of lettuce per 6-inch sandwich? How many slices of meat? What angle to cut the bread? It all comes back to what was engineered upstream. Without the highly standardized processes in the manufacturing plants, the in-store experience wouldn't feel as predictable and familiar across the world. The industrial journey of a Chipotle meal begins with ingredient sourcing. Chipotle is known for its emphasis on food with integrity, which means that much of the upstream processing is tightly controlled, even before the factories get involved. The chain sources meats that are often antibiotic-free, pasture-raised, or sustainably farmed. These meats arrive at centralized processing plants, some Chipotle-operated, others contracted to third-party co-packers, with exacting specifications. Take chicken, for instance, one of Chipotle's most popular proteins. Whole chicken breasts and thighs are delivered from certified suppliers in refrigerated transport and immediately placed into cold storage bays at the processing facility. These facilities are equipped with advanced sanitation systems, including antimicrobial entry zones and HEPA-filtered air circulation to maintain a sterile environment. The chicken is deboned, trimmed of excess fat, and portioned into standardized sizes using automated cutters. Optical sorters with high-speed cameras and laser detection systems inspect each piece for defects, bone fragments, or inconsistencies. After cutting, the chicken moves into industrial tumblers or vacuum mixers where it is marinated. The marinade consists of oil, spices, garlic, citrus juices, and chipotle pepper, all pre-mixed in large blending tanks. These tumblers are designed to evenly coat the chicken while tenderizing it, using a slow rotational motion that lasts anywhere from 20 minutes to several hours, depending on the specific formulation. The chicken is then sealed into vacuum-packed pouches or bulk containers and flash-chilled. In many cases, the chicken is shipped raw to Chipotle locations, where it is grilled fresh daily. However, in higher volume markets or during peak operational periods, some portions may be pre-cooked using commercial-grade combi ovens or grill presses inside regional commissaries. These ovens are steam-injected and heat-distributed, ensuring that the chicken reaches internal temperatures of 165 degrees without losing moisture. After cooking, the chicken is cooled through rapid chill spiral systems that reduce the temperature below 40 degrees in less than 90 minutes, in compliance with USDA food safety standards. Now let's move to beef, specifically the barbacoa and steak options. These are handled in meat facilities equipped to manage tougher cuts like shoulder clod or round for barbacoa, and sirloin or top butt for steak. The barbacoa beef is typically seasoned, seared, and slow cooked in massive steam kettles or pressurized braising tanks. These tanks operate on programmable logic controllers that maintain precise temperatures and cook times, allowing the meat to tenderize while absorbing the bold, chipotle, and cumin flavors characteristic of the dish. Once fully cooked and shredded by automated paddles, the barbacoa is portioned into pouches and vacuum sealed. It's then rapidly frozen using cryogenic tunnel freezers, often with liquid nitrogen or CO2, to preserve texture and moisture content. Steak, on the other hand, may be seared and sous vided, then chilled and packaged for final grilling in store, allowing for that signature charred flavor upon finishing. Beans, both black and pinto, are another central component of Chipotle's offerings, and their factory preparation is highly systematic. Dry beans are received in bulk sacks and stored in silo bins, where they undergo cleaning, sorting, and rinsing. Industrial bean cookers, large rotating steam kettles or pressure vessels, hydrate and cook the beans using temperature and pressure sensors to ensure that every batch hits the ideal softness and moisture level. Chipotle's beans are often seasoned with bay leaf, garlic, cumin, and salt, and held in stainless steel jacketed tanks for blending. After cooking, beans are cooled, portioned into food-safe containers or sealed bags, and transported under refrigeration to stores, where they are reheated and seasoned further before serving. Some regional commissaries may do the final seasoning step in-house, using proprietary spice blends and steam kettles to reduce in-store labor. Next up is the rice. Salsas, like the mild tomato salsa, corn salsa, and spicy red chili version, are produced in facilities that combine both fresh vegetable processing and sauce manufacturing capabilities. Roma tomatoes, tomatillos, onions, and jalapenos are washed, diced, and de-seeded by high-speed dicers equipped with antimicrobial wash cycles. The chopped ingredients are portioned into blending tanks, where citrus juice, cilantro, salt, and spices are added. These tanks are chilled to preserve freshness during mixing. The salsas are filled into containers using multi-head fillers, which ensure precise weight and avoid overfilling. Each container is lidded, labeled, coded, and passed through X-ray or metal detection systems before being boxed and shipped under refrigeration. Because Chipotle prides itself on using fresh, preservative-free salsas, the cold chain must be rigorously maintained, and shelf life is generally short, often under 7 days. Guacamole is arguably one of Chipotle's most iconic items, and it, too, is partially factory-produced to reduce in-store prep time. Avocados are shipped to processing plants where they are ripened in ethylene-controlled ripening rooms. Once they reach optimal softness, they are halved, pitted, and scooped using semi-automated systems. Some facilities still rely on manual scooping to preserve texture and quality. The avocado pulp is then mixed with red onions, cilantro, lime juice, salt, and jalapenos in large mixing vessels outfitted with slow-speed paddle blades to avoid over-pureeing. The finished guacamole is portioned into food service containers and sealed under nitrogen-rich modified atmosphere packaging to prevent oxidation. These are chilled and shipped directly to stores, where they are used within a few days. Even toppings like shredded cheese and lettuce are processed off-site. Cheese blocks, such as Monterey Jack and white cheddar, are shredded using rotary shredders that minimize clumping and deliver consistent length and thickness. The shreds are dusted lightly with starch or cellulose to prevent sticking, and then packaged in gas-flushed bags. Lettuce, typically romaine, is shredded, washed, triple rinsed, and run through centrifugal dryers before being packed in bulk bags with breathable liners. All of these components, once prepared, are transported through a tightly managed distribution network. Refrigerated trucks, monitored with GPS and temperature sensors, deliver ingredients to regional distribution centers or directly to restaurants. There, store teams receive shipments, log temperature compliance, and rotate stock to maintain freshness. From an industrial standpoint, the brilliance of Chipotle's system lies in its hybrid model. It doesn't fully outsource prep, nor does it rely completely on in-store